June 6, 1944, 11:45 a.m., off Gold Beach, Normandy. Lieutenant Commander John Hughes Hallett of the Royal Navy stood on the bridge of HMS Bulolo, watching something that defied every principle of harbour engineering he had learned in 20 years of naval service. Spread across 3 miles of open water, massive concrete structures the size of apartment buildings were being positioned with mathematical precision. Steel pierheads weighing over 1,000 tons, each floated like corks, connected by flexible roadways that rose and fell with 18-foot tides without breaking. Within 72 hours, these floating sections would form a complete artificial harbour capable of handling cargo ships that normally required permanent stone quays built over decades. The harbour would unload Liberty ships in 90 minutes rather than the 3 days required using conventional beach methods. What Hughes Hallett was witnessing would prove more crucial to Allied victory than the soldiers who had stormed these beaches at dawn. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of this impossible harbour began not with triumph, but with catastrophe. August 19, 1942, Dieppe, France. The Canadian 2nd Division attempted an amphibious assault on this heavily fortified port, believing that capturing harbour facilities intact was essential for maintaining troops ashore. The operation lasted 9 hours and cost 2,900 casualties. Of the 5,000 Canadians who landed, only 1,500 returned to England unharmed. The lessons were devastating and immediate. Admiral Louis Mountbatten, Chief of Combined Operations, stood in the operations room at Portsmouth as reports filtered back from the disaster. His aide, Lieutenant Colonel Jock Lawrence, recorded Mountbatten's assessment in the official after-action report that would reshape Allied strategy. The Germans will defend every port with fanatical determination. We cannot capture harbours intact against determined resistance. If we cannot capture harbours, we must bring harbours with us. Churchill received Mountbatten's preliminary report on August 20th. His response, scribbled in red ink across the bottom of the document, launched the most audacious engineering project of the war. If we cannot capture harbours, we shall construct them. Direct the Admiralty to investigate artificial harbour construction immediately. Priority absolute. The concept seemed insane to conventional harbour engineers. Permanent harbours required massive stone breakwaters built over years, deep water quays founded on bedrock, and sophisticated dock facilities designed to last centuries. The Allied proposal was to build temporary harbours from floating sections, tow them across the English Channel, and assemble them off beaches that had never seen anything larger than fishing boats. The man tasked with making this impossible vision reality was Rear Admiral William Tennant, a naval engineer who had supervised the evacuation of Dunkirk and understood better than most the challenges of operating without proper harbour facilities. His first meeting with Churchill in September 1942 revealed the Prime Minister's characteristic impatience with conventional limitations. Tennant presented preliminary studies showing the enormous difficulties involved in constructing artificial harbours. Churchill's response was typically blunt. "The difficulties are obvious, Admiral. Solutions are what I require. You have until D-Day to design and build floating harbours capable of supplying 2 complete armies." The timeline seemed impossible, but Tennant had learned not to argue with Churchill when his mind was made. The technical challenges were staggering. Traditional harbours relied on permanent breakwaters that absorbed wave energy through sheer mass. The artificial harbours would need breakwaters that could be towed across the channel, positioned accurately in rough seas, and anchored securely enough to protect cargo ships during winter storms. The harbours would need deep water berths where Liberty ships could unload directly onto piers, connected to shore by roadways that remained functional despite 18-foot tidal ranges. Everything had to be designed for rapid assembly by naval crews under combat conditions, built to precise specifications despite wartime material shortages, and transported across 100 miles of open ocean where German submarines and aircraft operated freely. Tennant assembled a team of Britain's most capable engineers, but their initial assessment was sobering. Hugh Iores Hughes, chief engineer for the project and a specialist in marine construction, delivered his preliminary report in October 1942. "The physics are manageable, but the scale is unprecedented. We must design, build, and deploy harbour facilities equivalent to the Port of Dover in 18 months using materials and labour already committed to other war production. Traditional construction methods are inadequate. We must invent new approaches to every aspect of the problem. The breakthrough came from an unexpected source. Alan Beckett, a civil engineer who had spent his career building bridges rather than harbours, suggested treating the artificial harbours not as permanent installations, but as floating bridges extended into deep water. His concept was revolutionary. Instead of fighting the ocean's movement, the harbour would move with it. Beckett's design used articulated sections connected by flexible joints that allowed the entire structure to rise and fall with tides while maintaining operational capability. Cargo ships would moor to floating pierheads that moved with the waves rather than resisting them. Roadways connecting the pierheads to shore would be supported by floating pontoons that accommodated tidal changes automatically. The Admiralty's Director of Miscellaneous Weapons Development, a deliberately vague title that concealed some of Britain's most innovative wartime projects, authorised Beckett to build a quarter-scale prototype in the Solent during November 1942. The test results exceeded expectations. The floating pier system remained stable in rough seas, cargo handling proceeded smoothly despite wave action, and the entire structure could be assembled by unskilled crews in hours rather than days. Admiral Tennant witnessed the tests personally and immediately authorised full-scale development. His report to Churchill was uncharacteristically optimistic for a Royal Navy officer. The concept is sound. Engineering challenges remain formidable, but solutions appear achievable. Recommend immediate authorisation for full development with highest priority for materials and labour. Churchill's response came within hours. Approved. Codename Mulberry. Inform no one outside immediate development team. By December 1942, 2,000 engineers and technicians were working on Mulberry components at secret facilities across Britain. The project required innovations in every aspect of harbour construction. The breakwaters needed to be massive enough to absorb Atlantic storm energy, yet light enough for ocean transport. The solution was revolutionary concrete construction, using hollow chambers that provided strength with reduced weight. Each breakwater section, designated Phoenix units, measured 200 feet long, 60 feet wide, and 60 feet high. The concrete walls were 6 feet thick at the base, tapering to 3 feet at the top. Internal chambers were divided by watertight bulkheads, allowing sections to survive damage and remain afloat even if partially flooded. When positioned and flooded deliberately, each Phoenix unit displaced 6,000 tons and provided the mass needed to absorb wave energy effectively. 20 Phoenix units arranged in proper sequence would create a breakwater 3 miles long, enclosing sufficient deep water for dozens of cargo ships to operate simultaneously. The engineering was elegant, but the construction challenges were enormous. Each Phoenix unit required 1,400 tons of concrete, 40 tons of steel reinforcement, and precision construction to tolerances measured in inches rather than feet. Traditional concrete construction used fixed forms on stable foundations. The Phoenix units were built in specially constructed dry docks that could be flooded to float the completed sections. 6 construction sites along the Thames and at ports throughout southern England worked simultaneously, each producing Phoenix units at the rate of 1 per week. The floating pierheads presented different challenges. These massive steel structures, designated whale units, measured 200 feet long and 60 feet wide, weighing over 1,000 tons each. They functioned as floating platforms where cargo ships could moor in deep water for direct unloading onto trucks and trains. The pierheads incorporated sophisticated mooring systems, cargo handling equipment, and flexible connections to the roadway system. Most crucially, they were designed to remain level despite wave action through a system of stabilizing chambers that automatically adjusted to sea conditions. The roadways connecting pierheads to shore were perhaps the most ingenious component. Designated beetle roadways, these floating sections were 40 feet wide and supported by steel pontoons every 20 feet. The roadway surface was steel planking capable of supporting 40-ton trucks at highway speeds. The pontoons were connected by flexible joints that allowed the roadway to follow wave motion without breaking, creating what engineers called a floating bridge that could extend up to 2 miles into deep water. The Beetle roadways incorporated an automatic adjustment system for tidal changes. As tides rose and fell 18 feet twice daily, the shore connections moved along inclined ramps, maintaining continuous roadway grades regardless of water level. The entire system was designed so that trucks could drive from cargo ships to inland supply dumps without interruption, despite being supported entirely by floating structures in open ocean. By March 1943, component production was accelerating across Britain. The Phoenix concrete units were being built at construction sites that had been automobile factories, shipyards, and aircraft plants 18 months earlier. Workers who had built Spitfire wings were now pouring concrete with the same precision they had applied to aircraft construction. The scale of production was unprecedented for marine construction. At peak output in early 1944, British factories were producing Phoenix units at the rate of 8 per week, Whale pier heads at 4 per week, and Beetle roadway sections at 60 per week. The floating harbour components consumed 17% of Britain's concrete production and 12% of steel output during the first quarter of 1944. Quality control was critical because every component would be tested under combat conditions, where failure meant the collapse of Allied logistics. Each Phoenix unit underwent pressure testing to verify watertight integrity, structural load testing to confirm it could withstand grounding forces, and flotation testing to ensure proper stability during ocean transport. The Whale pier heads were tested with simulated cargo loads, their mooring systems stressed to destruction limits, and their stabilization systems evaluated in artificial wave conditions. The Beetle roadway sections were tested with 40-ton trucks at various speeds and subjected to flexural stress testing that simulated storm conditions. Admiral Tennant established a test facility at Lymington, where full-scale harbour sections were assembled and operated under realistic conditions. Cargo ships unloaded supplies onto the floating piers, while artificial wave generators created storm conditions. The tests revealed numerous design flaws that were corrected before mass production began. The most critical discovery was that flexible joints in the roadway system required constant maintenance to prevent saltwater corrosion. The solution was a revolutionary lubricant system that automatically protected joint mechanisms, extending operational life from weeks to months. These tests probably saved the entire Mulberry project from failure during actual operations. Training crews to assemble and operate the floating harbours required months of preparation. The Royal Navy established special training facilities where sailors learned to position Phoenix units with precision despite wave action, connect Whale pier heads to anchoring systems under time pressure, and assemble Beetle roadways rapidly in rough seas. The complexity was staggering. A complete Mulberry Harbour required 60 Phoenix breakwater units, 20 Whale pier heads, and over 200 Beetle roadway sections, all positioned with mathematical precision in predetermined locations. The assembly crews had to complete this massive construction project while under enemy fire, in rough seas, working around the clock with minimal margin for error. Lieutenant Commander David Bruce, who commanded one of the assembly teams, described the training in his post-war memoir published in 1958. "We practiced until we could position a 1,000-ton concrete unit within 6 inches of its designated location in complete darkness. Failure was not an option. The success of the invasion depended on our ability to build functional harbours faster than the Germans could destroy them." By May 1944, over 10,000 naval personnel had been trained in Mulberry assembly operations. Component stockpiles filled every available space in southern England. Phoenix units floated in tidal basins awaiting final positioning. Whale pier heads sat on specially constructed launching ways ready for transport. Beetle roadway sections were stacked in enormous warehouses near Portsmouth and Southampton. The logistics of moving Mulberry components to Normandy were as complex as the engineering. Each Phoenix unit required a dedicated ocean-going tug and specialized equipment for precise positioning. The Whale pier heads needed heavy lift ships capable of carrying 1,000-ton loads across the channel in rough seas. The Beetle roadway sections could be transported on conventional cargo ships, but required immediate assembly upon arrival. Transportation planning assumed that German aircraft and submarines would attack the slow-moving convoys carrying Mulberry components. Each Phoenix unit took 18 hours to tow from England to Normandy, moving at less than 3 knots to prevent structural damage. The convoys were essentially immobile targets for 12 hours, requiring massive naval and air protection throughout the journey. Winston Churchill personally inspected Mulberry components during a secret visit to Portsmouth in late May 1944. His reaction, recorded in his private secretary's diary, revealed both his satisfaction with the project and his anxiety about its success. These floating harbours represent our greatest gamble. If they succeed, we can supply 2 armies indefinitely without capturing a single port. If they fail, the invasion may fail with them. The Prime Minister's concerns were justified. The entire Allied strategy for Northwest Europe depended on the ability to land and supply massive forces across open beaches. Traditional military wisdom held that major amphibious operations required the rapid capture of port facilities to handle the enormous quantities of supplies needed by modern armies. The Germans had fortified every port along the Atlantic Wall with fanatical determination, understanding that denying harbours to the Allies would cripple any invasion attempt. Hitler's Atlantic Wall construction focused primarily on port defences for exactly this reason. Field Marshal Erwin Rommel had inspected every harbour from Norway to Spain, strengthening defences and preparing demolition charges that would destroy dock facilities if capture seemed imminent. The Mulberry Harbors represented a complete circumvention of German defensive strategy. Instead of assaulting heavily fortified ports, the Allies would simply ignore them, creating their own harbours wherever they chose to land. The strategic implications were profound, but everything depended on whether floating concrete structures could withstand Atlantic storms and enemy attacks while handling cargo volumes equivalent to major ports. D-Day morning brought the ultimate test. As Allied forces stormed the Normandy beaches, specially trained Royal Navy crews began positioning the first Mulberry components in predetermined locations off Arromanches and Omaha Beach. The assembly operations proceeded under enemy artillery fire, with German aircraft attacking throughout the day and night. The first Phoenix units were positioned successfully, despite rough seas and enemy action. Within 24 hours, preliminary breakwaters were providing shelter for cargo ships, attempting to unload supplies directly onto the beaches. The floating pierheads arrived on D+1 and were connected to the breakwater systems by D+2. By D+3, the first Beetle roadways were operational, allowing trucks to drive directly from cargo ships to shore without using landing craft. The time saved was extraordinary. Previously, cargo ships had anchored offshore while landing craft shuttled supplies to the beach in small loads, requiring 3 days to unload a typical Liberty ship completely. With the Mulberry Harbors operational, the same ships were unloaded in 90 minutes using conventional dock procedures. The efficiency gains were revolutionary and immediately decisive for the battle ashore. Allied forces received supplies faster than had been considered possible without capturing major ports intact. The German reaction was swift and desperate. Luftwaffe attacks concentrated on the floating harbours, recognizing their critical importance to Allied operations. German artillery attempted to range the harbour facilities from inland positions. Submarine attacks targeted the slow-moving Phoenix units during transport operations. Despite these attacks, the Mulberry construction proceeded according to schedule. Royal Navy crews demonstrated remarkable skill positioning massive concrete units while under fire. The flexible design of the harbour systems absorbed battle damage effectively, with individual Phoenix units able to continue functioning even after sustaining direct hits from artillery or aircraft bombs. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Admiral Ramsay, commanding naval operations for the invasion, reported to Churchill on June 10th that both Mulberry Harbors were approaching full operational capacity ahead of schedule. His assessment would prove prophetic regarding the strategic impact of the artificial harbours on Allied logistics and German defensive planning. The floating harbours have exceeded all expectations. Cargo throughput is 30% higher than projected. German attacks have caused minimal operational disruption. Most significantly, we are supplying 2 complete armies without requiring a single captured port. The strategic situation has been reversed completely in our favor. The success was almost too good to believe. By June 15th, Mulberry A at Omaha Beach was handling 8 Liberty ships simultaneously, unloading them completely in sequences that took less than 2 hours per vessel. Mulberry B at Arromanches was processing 12 ships daily, moving cargo volumes that exceeded many permanent peacetime ports. The statistics were staggering. In the first 10 days of operation, the 2 artificial harbors had handled over 150,000 tons of supplies, 60,000 vehicles, and 400,000 troops. The flow of materials was so efficient that supply dumps inland were overflowing faster than transportation networks could distribute the cargo. Lieutenant Colonel James Hutchinson, Chief Logistics Officer for the 21st Army Group, documented the transformation in Allied capabilities in his daily reports to Montgomery's headquarters. The artificial harbors have eliminated our logistics bottleneck completely. We are now limited by inland transportation capacity rather than harbor throughput. The Germans designed their defensive strategy, assuming we would require captured ports. That assumption has been proven catastrophically wrong. But on June 19th, nature intervened with devastating force. A massive storm system moving across the North Atlantic generated winds exceeding 60 miles per hour and waves reaching 20 feet in height. The storm lasted 3 days and subjected the Mulberry Harbors to stresses far beyond their design specifications. The flexible connections that had been the harbor's greatest strength under normal conditions became their greatest vulnerability under extreme stress. Beetle roadway sections began breaking apart as flexible joints exceeded their movement limits. Whale pier heads broke free from their moorings and collided with each other and with cargo ships. Most catastrophically, several Phoenix breakwater units were driven from their positions, opening gaps that allowed storm waves to enter the harbor areas and destroy everything inside. Mulberry A at Omaha Beach suffered complete destruction. The harbor that had been processing 8 ships simultaneously was reduced to scattered wreckage spread across 5 miles of coastline. Admiral Tennant, observing the destruction from HMS Bulolo, watched 18 months of engineering effort disappear in 72 hours. His report to the Admiralty, written as the storm subsided on June 22nd, captured both the scale of the disaster and the resilience of the engineering concept. Mulberry A is a total loss. All major components have been destroyed or displaced beyond recovery. Estimated reconstruction time 6 weeks minimum. However, Mulberry B at Arromanches has survived with approximately 60% operational capacity intact. Most significantly, the surviving Phoenix units have proven the fundamental soundness of the design. The harbor was destroyed by conditions exceeding design parameters, not by inherent flaws. Churchill's reaction to news of the storm damage was characteristic. His immediate telegram to Tennant read simply, "Rebuild immediately. Maximum priority for materials and personnel. The Germans must not be allowed to benefit from this natural disaster." But rebuilding Mulberry A would take weeks that the Allied forces did not have. The German army was rushing reinforcements toward Normandy, and the window for breaking out of the beachhead was closing rapidly. The Allied supply situation had become critical once again. The solution came from an unexpected source. Instead of rebuilding the destroyed harbor, Admiral Tennant proposed cannibalizing its salvageable components to strengthen and expand Mulberry B at Arromanches. Phoenix units that had been driven ashore but remained structurally intact could be refloated and repositioned. Whale pier heads that had suffered damage but remained functional could be repaired and integrated into the surviving harbor. Most importantly, Beetle roadway sections scattered along the coastline could be recovered and used to extend Mulberry B's capacity far beyond its original design specifications. The concept was audacious. Instead of operating 2 moderate-capacity harbors, the Allies would concentrate all resources on creating one massive harbor capable of handling cargo volumes equivalent to the Port of London. The reconstruction and expansion of Mulberry B proceeded with desperate urgency. Royal Navy salvage crews worked around the clock to recover usable components from the wreckage of Mulberry A. Specialized lifting equipment was brought from England to refloat Phoenix units that had been driven onto the beaches. The expanded harbour that emerged from this reconstruction effort was larger and more sophisticated than either of the original Mulberry designs. It incorporated lessons learned from the storm damage, with stronger connections between floating sections and improved anchoring systems for the breakwater units. By July 1st, the rebuilt and expanded Mulberry B was operational at unprecedented capacity. The harbour could now handle 24 cargo ships simultaneously, more than double its original design capacity. Unloading times had been reduced to an average of 75 minutes per Liberty ship through improved cargo handling procedures and additional pierheads. The psychological impact on German forces was profound. Field Marshal Rommel's intelligence reports documented German amazement at the Allied ability to maintain massive supply flows without capturing any ports. German defensive planning had been based entirely on the assumption that denying ports to the Allies would strangle their logistics. Rommel's assessment, found in captured German documents after the war, revealed the strategic confusion the Mulberry Harbors had created among German commanders. The enemy has constructed harbour facilities from nothing in a matter of days. Their supply capacity exceeds that of Cherbourg or Le Havre, using temporary structures that appear and disappear at will. Our defensive strategy has been rendered obsolete by engineering capabilities we did not believe possible. The expanded Mulberry B became the backbone of Allied logistics for the remainder of the Normandy campaign. Through the summer of 1944, the artificial harbour handled cargo volumes that sustained 2 complete army groups advancing across France. The statistics were extraordinary even by modern standards. During peak operations in July 1944, Mulberry B processed an average of 11,000 tons of supplies daily. This exceeded the pre-war cargo capacity of most European ports and was achieved using temporary structures that had been assembled in hostile waters under enemy fire. The harbour handled specialized cargo that would have been impossible to land using conventional beach methods. Tank transporters carrying Churchill tanks were driven directly from cargo ships onto the floating roadways. Artillery pieces weighing up to 8 tons were moved from ship to shore without using cranes. Fuel tankers delivering aviation gasoline were connected directly to flexible pipelines that carried fuel inland to airfields. Perhaps most remarkably, the harbour operations continued through conditions that would have halted activity at permanent ports. During rough weather, the floating pierheads automatically adjusted to wave action, maintaining stable platforms for cargo operations. When tides changed 18 feet twice daily, the automatic adjustment systems in the roadway connections maintained continuous access without interrupting operations. Major General Sir Miles Graham, Chief Administrative Officer for the 21st Army Group, summarized the strategic impact of Mulberry B in his final report on Normandy logistics, submitted in September 1944. The artificial harbour has enabled operations that conventional military wisdom considered impossible. We have sustained 2 army groups advancing 400 miles inland, using a temporary harbour built from floating sections in hostile waters. The implications for future amphibious operations are revolutionary. The German response to the Mulberry Harbors evolved from initial disbelief to desperate attempts at destruction. Luftwaffe attacks concentrated on the harbour facilities throughout the summer, recognizing their critical importance to Allied operations. German artillery attempted to range the floating structures from positions inland. Most innovatively, the Germans deployed human torpedoes and midget submarines in attempts to attack the harbour from underwater. These desperate measures achieved minimal success against the floating structures, which proved remarkably resilient to explosive damage due to their compartmented construction and flexible connections. The failure of German attacks on Mulberry B demonstrated a crucial advantage of floating harbour construction over permanent installations. Traditional harbours concentrated vital functions in fixed structures that could be destroyed by precision attacks. The artificial harbours distributed functions across dozens of floating sections, any of which could be damaged without crippling the entire facility. When individual Phoenix units were damaged by German attacks, they could be replaced within hours using spare components. When whale pierheads were put out of action, cargo operations continued using the remaining platforms. The modular design that had enabled rapid construction also provided unprecedented operational resilience. By August 1944, Allied forces had broken out of the Normandy beachhead and were advancing rapidly across France. The capture of Cherbourg and other ports began reducing dependence on the artificial harbours, but Mulberry B continued operations at high capacity to support the expanding Allied logistical requirements. The harbour's final statistics for the Normandy campaign were extraordinary. From D-Day through the end of August 1944, Mulberry B handled over 2.5 million tons of supplies, 500,000 vehicles, and 3 million personnel. These figures represented approximately 60% of all Allied logistics for the Normandy campaign. More significantly, the artificial harbour had enabled the rapid build-up of forces that made the breakout possible. Without the massive cargo capacity provided by Mulberry B, Allied forces would have remained constrained in a narrow beachhead, while German reinforcements arrived to contain them. General Omar Bradley, commanding the First Army during the breakout operations, reflected on the strategic importance of the artificial harbours in his post-war memoir published in 1951. The Mulberry Harbors were as crucial to victory in Normandy as any tactical innovation of the war. They enabled us to supply forces at a scale and speed that the Germans could not match or counter. Without them, we might still have been fighting for the Cotentin Peninsula when winter arrived. The technological innovations developed for the Mulberry project influenced marine engineering for decades after the war. The flexible joint systems used in the Beetle roadways became standard components in floating bridge construction. The compartmented design of the Phoenix units influenced breakwater construction worldwide. Most significantly, the concept of modular harbour construction proved that temporary facilities could match or exceed the capacity of permanent installations when properly designed and operated. This realization transformed thinking about port construction, disaster relief operations, and military logistics. The post-war careers of Mulberry engineers demonstrated the lasting value of their wartime innovations. Alan Beckett, who had conceived the flexible roadway system, became a leading authority on floating bridge design and consulted on major civil engineering projects across Europe and Asia. Hugh Iris Hughes continued developing modular harbour concepts for commercial applications, designing floating terminals for oil exploration and cargo handling in remote locations. His techniques were used in offshore oil platform construction and floating airport proposals through the 1970s. Admiral William Tennant was promoted to full admiral and served as controller of the Navy after the war, applying lessons learned from Mulberry construction to peacetime naval engineering projects. His insistence on rigorous testing and quality control became standard practice in Royal Navy procurement. The workers who had built Mulberry components carried their specialized skills into peacetime construction projects. The precision concrete work required for Phoenix units influenced post-war building techniques. The steel fabrication methods developed for whale pierheads found applications in bridge construction and industrial facilities. Most importantly, the integrated workforce that had produced Mulberry components demonstrated the effectiveness of rapid training programs and skilled supervision. Women who had learned precision welding for harbour construction continued in manufacturing careers that had been closed to them before the war. The strategic lessons of the Mulberry Harbors extended far beyond their immediate tactical success. The project proved that industrial capacity could be rapidly redirected to solve unprecedented problems when necessity demanded it. Britain had transformed automobile factories into precision concrete plants and aircraft manufacturers into specialized steel fabricators within months of receiving requirements. The artificial harbors demonstrated that conventional wisdom about engineering limitations often reflected organizational constraints rather than physical impossibilities. Naval engineers had spent decades believing that major harbors required permanent construction and years of building time. The Mulberry project proved that temporary installations could exceed permanent facilities when innovative design was combined with adequate resources. Perhaps most significantly, the floating harbors showed that strategic problems could be solved by circumventing them entirely rather than confronting them directly. Instead of assaulting heavily fortified ports, the Allies simply built their own harbors wherever they chose to land. This approach transformed amphibious warfare and influenced military planning for generations. The final vindication of the Mulberry concept came in November 1944, when Allied forces finally captured the major port of Antwerp intact. Despite having access to one of Europe's finest harbours, Allied logistics officers discovered that Mulberry B was still handling cargo more efficiently than the permanent facilities at Antwerp. The artificial harbour's flexibility, modern cargo handling equipment, and optimized layout actually provided superior performance compared to a port designed decades earlier according to traditional concepts. This comparison validated every aspect of the revolutionary engineering that had seemed impossible just 2 years before. Mulberry B continued operations until December 1944, when the advance of Allied forces had progressed far enough inland that the Normandy harbour was no longer strategically necessary. The harbour was gradually dismantled, with components either returned to England for reuse or transferred to other theatres where artificial harbours were needed. Some Phoenix units were towed to the Pacific, where they formed breakwaters for operations against Japanese-held islands. Whale pier heads were converted to floating docks for naval bases in remote locations. Beetle roadway sections found new uses as floating bridges for river crossings and amphibious training facilities. The legacy of the Mulberry Harbors extended far beyond their wartime service. The National Institute of Oceanography used Mulberry engineering data to develop civilian applications for floating structures. Offshore oil exploration adopted modular construction techniques derived from Phoenix unit design. International disaster relief organizations studied Mulberry assembly procedures to develop rapid response capabilities for humanitarian emergencies. The concept of prefabricated harbor components that could be transported quickly to any location influenced port construction in developing nations throughout the post-war era. Today, visitors to Arromanches can still see remnants of Phoenix units from Mulberry B. These massive concrete structures, now serving as artificial reefs, remain exactly where Royal Navy crews positioned them in June 1944. Their presence provides tangible evidence of the engineering achievement that made Allied victory possible. The Mulberry Harbors Museum in Arromanches displays detailed models of the artificial harbour systems and explains their crucial role in the Normandy campaign. Interactive exhibits allow visitors to understand the scale and complexity of floating harbour operations, while preserved artifacts demonstrate the precision engineering required for success. The museum's most popular exhibit is a scale model of the complete Mulberry B harbour, showing all major components in their operational positions. Visitors can see how Phoenix breakwaters protected whale pier heads, how Beetle roadways connected deep water facilities to shore, and how the entire system functioned as an integrated harbour despite being built entirely from floating sections. Lieutenant Commander John Hughes Hallett, who had watched the first Phoenix units being positioned on D-Day morning, returned to Arromanches for the 40th anniversary of the landings in 1984. His reflection, recorded by the BBC, captured the lasting significance of what he had witnessed. We proved that engineering ingenuity could overcome any limitation when necessity demanded it. The Germans believed they had made invasion impossible by fortifying the ports. We made their fortifications irrelevant by bringing our own ports with us. That lesson applies to every challenge that seems insurmountable. The solution may not be to fight the problem directly, but to make the problem irrelevant through innovation. The story of the Mulberry Harbors demonstrates that the greatest engineering achievements often emerge from the most desperate circumstances. When conventional approaches prove inadequate, innovation flourishes. When traditional limitations are questioned, new possibilities emerge. The artificial harbors succeeded because engineers were willing to abandon everything they thought they knew about harbor construction and reimagine the entire concept from first principles. They proved that floating structures could be more effective than permanent installations, that temporary facilities could exceed the capacity of established ports, and that impossible schedules could be met when the stakes demanded it. Admiral Tennant's final assessment, written in his 1960 memoir, captured the essence of the Mulberry achievement. We succeeded not because we were smarter than previous generations of engineers, but because we were freed from their assumptions. When survival depends on innovation, conventional wisdom becomes a luxury we cannot afford. The Mulberry Harbors proved that human ingenuity, when properly directed, can overcome any obstacle that physics allows. The mathematics were simple but decisive. Mulberry B had handled 2.5 million tons of supplies in less than 3 months using temporary structures assembled under fire. Permanent harbors built over decades typically handled similar volumes in entire years. The artificial harbor had processed cargo faster, more efficiently, and more reliably than installations that conventional wisdom claimed were superior. Those statistics represented more than engineering success. They represented the transformation of strategic possibility. The artificial harbors had enabled operations that military planners considered impossible, supplied armies at scales that logistics experts deemed unachievable, and solved problems that conventional approaches could not address. The Phoenix units that still rest off Aramanches serve as monuments to human determination and engineering innovation. They prove that when necessity demands it, ordinary people can achieve extraordinary results by questioning what everyone knows to be impossible, and discovering that impossible often means merely difficult. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.